In this problem, you have two wires carrying two different currents, and they're both coming out of the plane of the page. They're separated by some distance d, and we're asked the two parts of this problem. First, we're asked to find the total magnetic field at point P1, which is halfway between the two wires, and then we are asked to find the magnetic field at point P2, which is a distance d above the wire on the right. We call that carrying current I2. So we know the currents through each of these wires. We know the distance. We just need to find the magnetic field at these 2 points. So let's look at A first. Find the field at magnetic field at point P1. Okay, so we'll use the second right-hand rule to find the direction, and then we have that that equation that we derived from Josevar's law for the magnetic field some distance away from a current carrying wire. First, let me draw this in a little greater detail. So we have this wire, and we have the second wire, and they're both coming out of the page. The currents are coming out of the page towards you. So this is I1, this is I2. So what is the direction of the field surrounding this wire on the left? Well, we know the field is going to circle around that wire. Which direction? Well, we only have two options. And since we're using a right-hand convention and the current is coming out of the page at you and your fingers are curling around in the direction of the field must be going around in this direction. So B1 travels in that direction. Well, the other wire has the same situation. The current's coming up out of the paper, so the field's curling around counterclockwise. So we can say B2 looks like that. So how are we going to find, so how do we construct the field, the total field at the center? Well, the total field is just the sum of B1 plus B2, where these are vectors. So I'm adding the vector bar here. So we have to think about the direction of the two. Well, this field is circulating counterclockwise as we step out this direction. It will still be circulating counterclockwise, and likewise on the other side, still going counterclockwise, but the difference is because of where you are in relation to the wires, the field from the first wire will be pointing straight up, and the field from the second wire will be pointing straight down at that position. So remember, the current's coming out of the page, the field circles in the direction with which you curl your fingers. So since you're curling your fingers this way, on this side of the wire, the field points straight up. On the other, for the other wire, the field points straight down. Now, if these two wires were carrying equal currents, these two fields would subtract out, and the total field at that point would be 0. But they are not carrying equal currents. So we have to look at the magnitude of each one. Well, if you remember, the magnitude of the magnetic field some distance away from a current carrying wire is mu naught I over 2 pi r, where r is the distance away from that wire. So we can construct an expression for B1. We say that's just mu naught I1 over 2 pi. Now what is r? R is the distance from the wire to the point of observation. The distance between the two wires is d, so r must be d over 2. And what is the direction? We'll say that's, given the convention, the right is positive I hat, up is positive j hat. So we can say that is in the positive j hat direction. Now, we note that I'm multiplying d over 2 times 2, so B1, I just simplify this a little bit, is mu naught I1 over pi d j hat. Likewise, we can say that B2 is just mu naught I2 over pi d because we're the same distance away from the wire 1 as we are wire 2. But this one's going to be in the negative j hat direction. So when we are asked to find the total field at point P1, that's just B1 plus B2. So the total field at point P1 is mu naught I1 over pi d j hat minus mu naught I2 over pi d j hat. Oh, lost a vector bar there. So I can factor out all the common terms and get mu naught over pi d times I1 minus I2 j hat. Which one has the larger current? That's I2, so this is going to end up being in the negative direction. If I put in the numbers for this, permeability of free space is 4 pi times 10 to the negative 7. I'm leaving the units out right now because I'm being a little lazy. Pi times 0.20 meters. I1's 3.0 amps minus 5.0 amps. Okay. And when you plug in the numbers, that is 4.00 times 10 to the negative 6 Tesla, and that is in the negative. Remember, the negative came from the subtraction, j hat direction. The next part of the problem wants us to find the magnetic field at some distance d above the wire on the right hand side. So let me sketch this again in a little more detail down here. So I've got a wire here, wire here. Let me make it a little larger. This is point P2. So if I look at the magnetic field from this first wire, remember that it's going to circle around the wire in a counterclockwise manner. So the magnetic field lines are going to look something like this. That means the magnetic field at this point right here is in this direction. The magnetic field from this wire directly beneath P2, again circling around, the lines would circle around in a counterclockwise fashion. Like this. So at point P2, the magnetic field points horizontally to the left. So we're going to need to break B1 down into X and Y components and add that to B2. So what is the magnitude of B2? Well, that one's simple because that's going to be in the negative I hat direction, the negative X direction, and it's going to have magnitude mu naught I2 over 2 pi times the distance away, which is d in the I hat direction. That one's simple. B1, a little bit more complicated. So then, we have this triangle. In this case, it's an equilateral triangle formed by these two wires because they're a distance d apart, and P2 is a distance d above, so that's an equilateral triangle. This angle equals that angle. This is the right angle, and you're looking for B1, which is at some angle above. Well, if we look at free body diagram, B1 makes some angle with the horizontal. What is that angle? Well, let's do some trigonometry here. If we extend the line of the triangle upwards, we'll know that this is also theta, which means this is theta. This is a 90-degree angle, so this angle would be 90 minus theta, but since it's an equilateral triangle, 90 minus theta just equals theta. The two angles are equal. So that means this angle theta. Okay, I'm going to break this down into x and y components. This is vector b1. So this is b1x, b1y, and the total vector b1 is of course b1x I hat plus b1y j hat. And that will be negative b1 cosine of theta I hat, because it's in the negative direction, and we get the magnitude by looking at the projection onto the x-axis by using cosine. And in the y direction, that's positive b1 sine of theta j hat. Well, what is, we haven't found theta yet. So we can't take cosine of it, but we don't even have to find theta. We can just find cosine of theta outright, because cosine of theta is adjacent over hypotenuse. The hypotenuse is d squared plus d squared, which is just root 2d. So cosine of theta is adjacent d over the hypotenuse, root 2d, or just square root of 2 over 2, because it's a 45-degree angle. And we know that sine of theta will give us the same result. Okay, so b1, I can factor out just this magnitude b1, and that leaves me with negative cosine of theta, which is root 2 over 2 I hat, plus sine of theta, which is root 2 over 2 j hat. Well, I can factor that even more and say this is b1 times root 2 over 2 negative I hat plus j hat. So then the magnitude of b1 is mu naught I1 over 2 pi times the distance away, which is root 2d. And then, of course, we have to include our square root of 2 over 2 and negative I hat plus j hat. Okay, I can simplify this quite a bit, I think. Okay, the square root of 2 cancels out. You end up with 4, so that's b1 equals mu naught I1 over 4 pi. Did I do that? D negative I hat plus j hat. So we need to add b1 and b2 to get the total magnetic field at P1. So it's B1 plus B2, or mu naught I1 4 pi D negative I hat plus j hat. That's B1 plus B2, which, where did we write that? All the way up here. So it's going to be a minus mu naught I2 over 2 pi d I hat. So now I can factor stuff up, make this stuff a little nicer. see, common to every term is mu naught over 2 pi d. For the I hats, it would be, let's see, negative I1, I1 over 2. So I1 over 2 gives me, yep, that's right, and minus just I2, I hat, plus 1 over 2 j hat. Oops, I'm sorry, I got out of the recording window. And I missed an I1 here. That's 1/2 times I1. Okay, so now it's just a matter of plugging in the numbers. 4 pi times 10 to the negative 7th Tesla meters per amps over 2 pi times d, which is 0.20 meters, minus I1, which is 3.00 amps over 2, minus I2, 5.00 amps, I hat, plus I1, which is 3.00 amps over 2 j hat. Okay, so you've got 1 times 10 to the negative 6 Tesla per amps times these two components. So that gives you negative 6.5. So this math is easy. 6.5 times 10 to the negative 6 Teslas, or micro Teslas, I hat, plus 1.5 micro Tesla. Again, same thing there. J hat.